Hello, once again. Welcome to 7.7. 7.7, multiplication, counting, principal, and permutations. Ooh, fancy. I know how boring that must sound. No, it's great. It's gonna be fun times. All right, here we go. 7.7. So multiplication, counting, principal. For a process involving multiple steps, R, we'll just denote as multiple. Suppose that there are n1 ways to do step one, and two ways to do step two, and and r ways to do step r. The total number of different ways to complete the process is n1 times n2 times all the way down to nr. So, for example, think of like probably talk about some examples like this, but like think of a combination lock or passwords or something like that. Let's start with the combination lock, right? Where you go 0 to 9, right? Let's say that there are 5 numbers on the combination lock, right? Give me a second. Okay, it felt longer than normal. Suppose there are 5 numbers on the combination lock. So there are 10 possibilities for the first number, right? Because 0 to 9, that's 10 numbers, 10 digits. There are, oh my goodness gracious, why do we do such things? Okay, there are, ugh, there are 10 ways to do step two, 10 ways to do step three, 10 ways to do the fourth digit, 10 ways to do the fifth digit. So you can find out how many total ways there are to how many different lock combinations there would be, basically, right? That's what this formula is saying. Okay. Alrighty then. Um, a permutation, a distinct arrangement of some groups. Let's see here. Distinct arrangement of some group of individuals where order matters. Order matters. So there's a notation for it, NPR, probability, where N represents the number of and R the number 4. We'll talk about that when we get to it. All right. That's going to be, well, we actually see the formula down there, so we'll get to that in a second. Factorial. Ooh, I love factorial. So factorial, so N factorial works like this. So um, N being whatever N is, so if it's 20, it's 20, right? Multiplied by N minus 1. So again, if N is 20, then N minus 1 would be 19, right? Multiplied by N minus 2, which would be like 18 if I was making that example, right? Uh, Multiplied all the way down till we got to 3, till we got to 2, till we got to 1. So I know the formula looks weird. That is n factorial is a product of the integers starting with n and going down to 1. So like as an example, just to give you, 6 factorial would equal 6 times 5 times 4 times 3 times 2 times 1, right? 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So whatever that factorial is, you start at that amount and you multiply every single number down to 1 all together. Does that make sense? Hopefully that makes sense. Calculate permutations. You can calculate the number of permutations of n individuals taken r at a time. So r is obviously got to be less than n. Using the multiplication counting principle or with the formula. So we'll see this again in our examples, but there's your formula. There's a calculator as well. I mean, it says right here. We'll talk about it. We'll probably use it. I'll probably show it to you momentarily, but yeah, permutation rule. Here we go. Let's look at an example. It'll make a little bit more sense probably. Online passwords help protect confidential information. One website allows users to choose a password that can consist of capital letters, lowercase letters, digits, or any of 4 special symbols. Those symbols. The only other requirement is that the first character of the password must be a letter. How many different 5-character passwords can be created? All right. Now, the way I would look at this is I would kind of, so we're making a password, 5 characters, 5 digits, right? 1 times 2 times 3 times 4 times 5. Now, remember, we can use capital letters, lowercase letters, digits, or any of the four special symbols. Now, the first one has to be a letter, right? Has to be a letter. We know that. Oops, come on. Why do we do stuff like this? Has to be a letter. But it doesn't say if it had to be a capital or lowercase letter. So if it could be either capital or lowercase, that would be 52 possibilities. Oh my goodness. This thing. Oh my gosh. So upset. Okay, 52 possibilities because 26 lowercase and 26 uppercase means that there's 52 possible ways I could do the first character of this password. Now the rest can be anything. Could be capital lowercase letter, could be a number, could be a symbol. Now, if you think about all the possible ways, right? We know, let's say again, lowercase, uppercase, number, or character. Look at how many different things we can have. I know I spelled character wrong, just get over it, okay? 26 lowercase letters, 26 uppercase letters, which is why we got 52 for the letter part, 10 digits, and then 4 special characters. Guess what? Add those up, and you have a total of 66 different types of characters for each slot. So there are 66, if you can use any of them, there's 66 possibilities for the second, there's 66 possibilities for the third, 66 possibilities for fourth, and 66 possibilities for the fifth. So how many combinations are there all together? Well, we got to multiply these all out. And if you multiply those numbers together, we have, ooh, it's a big number, 986,686,272 possible password combinations. Isn't that fantastic? I love that. That's great. All right, but that's the rule that we were kind of discussing up here, right? And I kind of demonstrated a little bit with my lock combination thing earlier. But I always set it up like this. I love setting it up like this. It makes it so much easier to remember how to do, right? I just want to know how many possibilities is it for this first slot? I think they call it the slot method, right? How many possibilities for the first slot? Possibilities for the second, possibility for the third. I set up these slots, and then I just, as soon as I know how much each slot is, I just multiply them together at the end, and it's great. So no formulas needed, just kind of like common sense in a way. It's not really common sense, but you know, it's a simplistic form. All right. At a track meet, 8 different hurdlers compete in the 400-meter hurdles. How many different ways are there for these runners to finish? Okay, this is where we're going to get to use our little formula, which is really nice. So we have 8 different runners, and obviously it says how many different ways can they finish. So I'm telling you right now, it's way too many to try and do individually, like keep count of. So we have our permutation formula basically, and this is where the factorials are going to come into play, I guess, as well. So again, think about the slot method, right? So 8 positions, 1, 2, 3, 4, 5, 6, 7, 8, 8. I almost did, I just kept going. So the first finisher, let's talk about first place, right? First place finisher, there could be 8 different people be the first place finisher, right? Now think about this though, right? Because whoever takes first place can't come in second, third, fourth, fifth, sixth, seventh, or eighth, right? Whoever finishes first can't be second, right? So that means there's 7 possibilities for someone to be in second. But remember, if they finish first and we have the first 2 finishers, then there's only 6 possible people to be the third finisher. Does that make sense? Because whoever finishes first and second are no longer capable of finishing third, etc. Right? You can kind of see where this trend goes. If you're first, second, or third, you've already finished. There's 5 possible people to finish fourth, right? And then 4, 3, 2, and 1, right? Hopefully that makes sense. Again, it's important to understand that if you finish first, right, and you've already finished, you can't be finishing second. So it's not, some people might be thinking it's 8 every time. right? It's not 8 every time because once you finish, it doesn't matter who it is, okay? Just again, it doesn't matter who it is. But once that person is finished, there's 7 other people that could finish second, right? And then et cetera, down the line. So this ultimately, right, as you're going to realize, this is why we invented factorials. 8 factorial is that. So on the calculator, we just simply figure out 8 factorial, which equals 40,320 possible finishing orders. Which is crazy. Absolutely crazy. But that's it, right? All right. Your school cafeteria has purchased enough food for 20 different lunches over the next 4 weeks. Due to a holiday on Monday, there are only 4 school days this week. How many different ways are there for the cafeteria to select and arrange 4 of these lunches to serve? Okay. So now this one's interesting because we're not using all 20 days, right? We have 20 options for lunch, but we only have 4 days, right, to choose from. Now, I assume we're not going to just serve the same thing every day, right? We're going to mix it up. So we have 20 different lunches over the next 4 weeks. So the first day, we have 20 possibilities, right? 20 possibilities that we can have for lunch. But the second day, because I've already used one of the possibilities, the second day is only going to have 19, right? And now because I've already used up 2 different lunches, the third day, there's only 18 possibilities that remain. And of course, the fourth day, there's 17 possibilities that remain. This is your slot method. This is going to be our total number of ways we could do it. 20 options for day 1, 19 other options for day 2, 18 options left for day 3, 17 options left for day 4. And this is going to come out to a grand total of 116,280 different arrangements that we could have here, right? 116,280 different possible arrangements. There you go. Now, even though I use the slot method to do this, I also want to demonstrate that this could have been done using the NPR formula that we were talking about earlier. So if you remember the formula from earlier, it said that this is equal to n factorial over, what was it? N minus r factorial. Let me just show you how this would work. N factorial would be 20 factorial, correct? N minus r would be 20 minus 4 factorial. Now, what would happen here is essentially we would have 20 factorial over 20 minus 4, which is 16 factorial. Now, just to showcase what this would be, remember 20 factorial would equal 20 times 19 times 18 times 17 times 16 times 15 times dot, 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 right? 16 factorial would be 16 times 15 times 14 times 13 times dot, dot, dot. Now, what would happen is the 16s would cancel out, the 15s would cancel out, the 14s would cancel, the 13s would cancel, obviously all the way down to 1 would cancel. So with that formula, the only values that wouldn't cancel out would be these 4, which is the same 4 that we used earlier. So that's the formula. And we can also see it on the calculator. Let me see if I can show you that real quick. The calculator, it's going to take a second to warm up. So just give it a moment. Yeah, I clicked it. I was like, did I click it? I did click it. It just takes a long time. All right. So your calculator has this ability as well. So you go to the math key, we go over to the probability tab. Oh, too far. You're going to see NPR, just like we said. And we're going to put 20 in for the possibilities and 4 for the ones that we're choosing. And there we go. 160,280. Very, very nice. So calculator can do it, and you can do it 2 different ways as well. So just to showcase the factorial button as well, 20, where's the factorial button? I gotta find it. I think it's in the math key. I think you have to hit it here. It's right here. I don't know if there's a shortcut for it or not. I have to look on the calculator closer. I'm sure it's somewhere, but anyway, we're just gonna move on. But you can hit 20 factorial, right? Remember, it was divided by 16 factorial. So let's go back, hit this, right? Same answer, right? So cool. So just wanted to point that all out. All right, we'll take that off. And that's going to do it for the 7.7 notes. We only got one more left before the test. So that's nice. I'll see you guys in 7.8. Bye for now.